science time. We're going to talk today about history of life. Let's write that down. The history, whoops, let's spell it right. History of life. I guess we're not really talking about the exact history of life. We're talking about how we know what we know about the history of life. So in general, can you tell me what could we say is the fundamental truth about life on Earth? It has done what over time?
Change.
Yes, exactly. So fundamentally, life on Earth has changed over time. The kind of a joking thing that we sometimes say is that the only thing that is constant in the universe is what?
Death.
No, it's not constant. Everything does what?
Grow.
Over time. It changes. The only thing that's constant is that everything changes. Everything is always in flux. The one fundamental truth we have about the history of life is that it was different before than it is now. What's some evidence for this? Well, what's some evidence for this? What do we see and first of all, how do we see back in time? We get in our time machine and we go we find fossils and what? What is our other primary piece of evidence for learning about the past of Earth?
Trace fossils.
Yeah, still fossils. So fossils and what are the substances?
Nowadays animals.
Environment.
Yeah, about what though?
Animals that used to
What other physical
animals
evidence?
that live today. That
Okay, that's true. That's true. We do use uniformitarianism. We can learn about the animals that used to live by the animals and organisms. I should be saying organisms. We don't only care about animals. We care about the organisms. We can learn about the organisms that used to live by looking at the organisms that are alive today. But also what? Besides the organisms, what other thing do we look at as physical evidence that tells us about the way Earth used to be?
Land.
Yes, say it better. What's the land made of? Primarily that we can look at rock. So we primarily look at fossils and we look at rock. Do you think that anyone cares about the history of the planet Mars?
No, probably
Not no one?
Well, some people.
Maybe.
Some people do, right? If we wanted to learn about the history of the planet Mars, what would we have to look at?
Look at
We have
Mars.
to look at the.
Look at
At the-
Mars. Look at the rocks.
As in rocks. Why?
Because
Because what isn't
Rocks
there?
have history of life.
No.
Or not life.
Maybe. We don't really know about Mars. Mars isn't a great example because on Earth we can look at the history of Earth by looking at the fossils and the rocks. On Mars, we can only look at the rocks because there aren't any fossils because there was nothing ever alive. That's not quite true. There is some evidence of bacteria on Mars, but we don't really know exactly what's going on there. But here's the point. Evidence that life has changed on Earth is that we look at fossils and we look at rocks, right? We look at fossils and we look at rocks. Write it down. Where are your notes, Colton? Oh, there you are. They're right there in front of you. Evidence of the earliest life forms. What might the earliest life forms have been? Dinosaurs before anything else that were dinosaurs?
bacteria.
Yeah, we're not talking about the earliest animal. We're talking about the earliest life was probably,
Bacteria.
maybe not even that complex. It must have been what?
It was like cells.
Yeah, it was cells. It was single cell. So the very first, if we look at the oldest fossils we can, right, and we'll talk about, or we had talked about with absolute age dating, there's methods through which we can tell within a certain degree of what's the word I want to use, precision. With a certain degree of precision, we can tell how old some of these fossils are. The oldest fossils we have are single-celled. Is there still single-celled life on Earth?
Mm-hmm.
Of course there is.
Yes.
But the oldest was single-celled. And well, first of all, what evidence? What lets us know that the oldest life was single-celled on Earth? Easy. What are the two pieces of physical evidence we have tells us that the oldest life was single-celled? Fossil evidence tells us the oldest life was single-celled. And then, how can we learn more about the single-celled life that used to be on Earth's surface? Well, we can look at their fossils, and we can look at the way single-celled life is now. To some extent, we can look at rocks, but what we're looking at is really the fossils and how single-celled organisms are now. And over time, when we look at the oldest rocks, we only see single-celled organisms. But over time, what happens to the life that we see? It becomes more what?
Advanced.
Yeah. More, let's say, complex. Advanced. We try not to use words like advanced when we're talking about fossils because it implies that, like, what would be the most advanced organism we can find in your opinion?
Monkeys.
No.
Yeah.
Try to make harder. Humans, probably, right? Humans are more advanced humans are more advanced. We don't say things like that because we try to keep it level, right? Just because human beings are the most complex organisms, which is true that we know of, doesn't mean they're better, right? Advanced is a word that makes it sound like better. But we use things like more complex. So the more recent fossils are
Humans.
multicelled,
Organisms.
and then eventually they branch out.
And then they become a rat, and that rat becomes a whale.
Sometimes, yeah. But listen, the problem with what you said, Justice, where you said a rat becomes a whale, is that there were rodents, and there are rodents today, and they have common ancestors of a whale. But the one rat did not you know what? I'm gonna have a whale day, and he just became a whale, right? The population of rodents, which are neither rats nor whales, diversified to form both rats and whales, right? So what we say is that, look at this. This is my drawing of a something. I made this intentionally bad. It's intentionally bad, so don't be mean to me. But rats, don't be mean to me.
Rats.
Oh, that's actually pretty good. I'm not gonna lie.
There we go. Rats,
Good.
shh, be nice to me.
That's just seems pretty
He
good.
was complimenting me.
Mr. Kind doesn't take compliments.
Yeah.
Oh yeah, that's sexy.
Don't say that bad word. Rats, mammals, and whales, mammals, have a common ancestor. This is a word we use a lot. They have a common ancestor. What's the word ancestor mean?
Old.
An old.
Like some
Your
there's something in the
great,
past.
great,
Yeah,
great,
yeah,
great,
right.
great
Your mommy is technically your ancestor, right? Your great 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 grandpa is one of your ancestors. An ancestor is organism further in the past that has led to you, right? Rats and whales and Justice
Oh boy, wow.
all have a common ancestor, right? Does that kind of make sense?
Yeah.
It isn't that one day one rodent woke up and was like, I'm going to be Justice. No, you would never say that. What a terrible mistake. What an awful mistake. No, but these things have a common ancestor, right? And in the same way that I was telling you guys about, this isn't, I know, I'm aware that there is controversy. That's a weird word to say. There's controversy about this, and there doesn't have to be, because what we're doing here is we're taking evidence, right? And we're applying the scientific method to it. And all the evidence points that this is true. And the controversy arises, as you're aware, when there is a perceived difference in one thing that you have or someone has been taught and another thing that you have been taught. And you're like, uh-oh, one of them's got to be right. I don't find that must be the case. I'm kind of being vague about this because I don't want to have letters written to me. It doesn't have to be controversial. It doesn't have to be. You can take the evidence and find that this is true, while also holding in your heart and mind that another thing is true too, right? That you can make them fit together. Do you understand what I'm saying? And even if you can't, this is what I'm encouraging to you. You're a person. I don't know if you're aware of that. You're a person, and what I want you to do is take the evidence you have of all of the kinds, of all the things you've been taught, take the evidence and make up your own dang mind, right? It doesn't have to fit the neat little cookie cutter way of thinking box A or the cookie cutter thinking way of box B, right? Take the evidence you have, look for new evidence, and make up your own dang mind. But make up your own dang mind, right? You don't take all the evidence you have and find a thing that works for you that fits with what you can understand and believe. Does that make sense to you?
Yes.
This does not have to be controversial, right? If you want to take all of the evidence I'm showing you and throw it out the window because you don't, you're uncomfortable with it, fine. If you are also, on the other end, you want to take all the evidence that someone else in some other capacity, I think you know what I'm talking about, has shown you, and make up your own mind, fine. If you want to believe none of it, right, and just make up your own thing that, like, we all sprang into existence this morning with all of our memories intact, fine. Whatever way the evidence fits your brain, I guess, whatever way the evidence fits your brain is fine. You make up your own mind, but guess what? When it comes time for the test, you better put in these answers that I'm telling you because that's what you're grading based on. I'm not trying to make you change your mind or have a different mind. Make up your own mind. But this is what the evidence suggests. Questions?
I used to be rat, and then I said go Power Rangers, and I became a human.
Yeah, right. So Power Rangers, that's a quick kind of evolution, right? The Power Rangers are like, go freaking Tyrannosaurus, and then they are.
I broke my entire.
But we call this process of life on Earth has changed over time. This, in one word, is easily, what is this? Say it, Colton.
Evolution.
Thanks, Colton.
You're welcome.
No.
That's all it has to be. That's all it has to be.
Orange.
That's all it has to be. Can we see some life evolve? Be careful, because growth is not the same thing as evolution. When one specific organism changes over time, that's called growth. When a population of organisms change over time, their traits, that's called evolution. Can we see this directly?
No.
Let me try again. Some, for instance, bacteria, things that reproduce very quickly, within the time that human beings have been observing them, some bacteria and viruses have evolved to do what? You're aware of this phenomenon.
COVID.
They've evolved to do what? Some bacteria, antibiotics no longer work on them because they've evolved to
live.
be
Resistant.
resistant to bacteria. That we call them superbugs. That is evolution. That is direct evidence for evolution. In the same way that there isn't a question about whether trees exist because we have direct evidence. We can go touch a tree, right? You can feel a tree. Same thing. We can feel one kind of evolution, which is that we can see bacteria populations change over time. We can see that. That is direct evidence. The rest of this we can think of as less direct evidence, which is fine. Like I said, whatever makes your little brain work the easiest. Take all the evidence you have and make up your own mind. Peyton.
So, well, not a question, I got a statement.
Yes, here.
So, I saw this thing the other day, and it was like, you can say Trump, and you can say Pelosi, you can say evolution is right.
Thank you, Peyton. That's very intuitive of you. We can all learn something from what Peyton said. Now let's try to learn something from the rest of this. Another piece of evidence that we have that life on Earth has changed. Obviously, we have fossils, and if we were to look at a fossil, the fossil record. Remember, we had the fossil record, which is kind of an exhaustive list of all the fossils that have ever been found. In general, we see that they do what? Fossils get over time, over geologic. What's that word geologic mean?
History.
When we're talking about geologic time, how is that different from time?
Earth.
Yeah, it's the history of Earth. Geologic time is different in its magnitude from regular time, right? When we're talking about time in our daily lives, we're like, oh, I don't have time for this. We're talking about, I don't have 5 minutes to talk to you about your problems, right? That's what time means to us. But when we talk about geologic time, we're talking about billions of years. We're talking about on the scale of, an enormous scale of billions of years. So over geologic time, fossils as evidence get what? In general, we find more and more what kind of fossils?
Get older.
Complex. Get more, thank you, Claire. Get more complex. And this tells us that life on Earth has changed over time, right? Why might, let's back up one more step. When we're talking about evolution, what gets passed on to the next generation?
Traits.
Your traits.
What specific
DNA.
traits? We call them,
Genetic.
the beneficial traits we call,
DNA.
no,
Genes.
come on, what do we call beneficial traits? No, I thought you said it. What do we call beneficial traits? We've been talking about this for a week now with our video.
Attributes.
No.
No. Artificial flavors.
Come on, you really should know this. Write this down. Adaptations. We call
Oh,
beneficial
I
traits.
said that.
Yeah, no, you didn't. We call beneficial traits adaptations. So why might the beneficial traits, the adaptations get passed on, cause organisms to become more complex?
What are they? Adaptation.
Compared to a single-celled organism, does a human being have more or fewer adaptations? Let's all be of one mind. Yeah, we have more adaptations. There's more. We're more complex because we have more adaptations. So that's why we see that fossils get more complex over time, is because they get more and more and more adaptations. The earliest, your book says, the earliest fossils that have been found are these single-celled cyanobacteria. Cyanobacteria. And these, how do you reckon that these things got their energy to live?
The
So the
sun.
first example of, and we call that,
Solar energy.
no, when they use the sun to make nutrients to survive,
Photosynthesis.
photosynthesis. So the first example of photosynthetic organisms are these cyanobacteria, and they were single-celled, and they existed in these mounds called stromatolites, which we'll talk about when you're in earth science. And then because of them, photosynthesis, what's made in photosynthesis? It takes, a plant
Energy.
takes what? Takes
Take
sunlight
the sunlight
and,
makes it ATPs.
no, what else does the plant take? Colton, you're smiling like you know it. What else? Photosynthesis takes sunlight and what else?
Nutrients. The water.
Water and,
ATP,
no, carbon dioxide.
Oh yeah, carbon dioxide.
Water, sunlight, and carbon dioxide, and it makes what two things?
Energy.
No. Well, yes, but in the form of sugar and oxygen. Write this down. So photosynthesis, you really should remember this. You really should remember this. Photosynthesis takes, listen, water, CO2, and it uses the sunlight
Okay, so what?
to make sugar and oxygen. Water plus CO2 in the presence of, God bless you, I put the sun over this arrow because that means in the presence of sunlight makes sugar, a specific kind of sugar called glucose, and oxygen gas. For a while, these organisms were, we certainly can't say that they were the only organism on Earth, but they're the only organism we have evidence for on Earth for a long period of time. And so they were doing this, just chugging away, drinking up the water, drinking up the CO2, looking at the sun, and making sugar so they could grow, and oxygen. And so over time, we call this the great oxygenation event because these organisms, great oxygenation event, these organisms made the Earth's atmosphere from about 1%, oxygen to about 25% oxygen over the course of 500 million years. All the oxygen we have on our planet now is because of photosynthesis. Not just photosynthesis, not just these things doing photosynthesis, but the photosynthesis from the trees and the algae and the moss that grow on planet Earth today. Yes, Kate? Yep.
remember to drink photosynthesis, keeping you alive.
Another thing that tells us that this idea of a common ancestor must be true is this idea of a transitional fossil. Transitional fossil. We find transitional fossils. What does the word transitional mean, probably?
Transitioning to.
Yeah, turning into. We find, what did you say? Yeah, change. The fossil that shows us the change between two. The best example, or the most famous example of this, is that there's a, this is in your book on page 32, but there's a fish with some little, like it's yeah, it's not legs, but it has little, it's supposed to be, it's its back ones. It's rear fins, it's what we call anal fins, nice. What we call the anal fins have the bones within them a little bit stouter. And that was probably, for this an adaptation of this organism. We just got done talking about adaptations organisms have. Why might the anal fins being stouter help this fish? Why might that be an adaptation? Wait, not swim faster, but what could it do if it was able to have more musculature in its rear limbs? It could do what with the ground that could, just like you when you're in the swimming pool, you can push off of the ground, right? So this thing with its stout anal fins could push off of the ground and go a little bit faster than things around it. An adaptation. It might escape from predators faster. It might be able to find a mate better. Whatever. This fish was called Eustenopton.
Eustenopton.
Eustenopton. Did I spell it right? Oh, Turon. Eustenopteron. Okay, you don't need to worry about how to spell this, but it has a name. This is a type of what?
Oh my god.
Hey, this is a type of what?
Fish.
Fish. How is this a transitional fossil? How is this different from other fish? It has these stout anal fins, right? All fish have anal fins, but this one has stout anal fins. I might even be using the wrong kind of fins. Hopefully I'm not, because I'm just saying the word anal over and over and over again. The next one, the next fossil that we have evidence for, that we can presume this Eustenopteron evolved into, is the Tiktaalik.
Take the what?
Tiktaalik.
Oh, there.
Did I spell it right? Oh, dang it, almost. Tiktaalik. Listen, this Tiktaalik was longer, flatter, and its fins were,
that what turns
both its
into a
front and
crocodile?
rear fins were stouter.
It turns into a crocodilian.
A crocodile. This is what it looks like.
And then over time, that population, because this was an advantage, how is it advantageous for these things? Well, they were probably able to escape predators. It's thought that the Tiktaalik could, for limited amounts of time, be out of the water. It could use its stout fins to move onto land. How might that be beneficial? How is that an adaptation?
Lay their eggs.
Probably not, maybe. No one knows. At least as far as I know, no one knows. How else might it be beneficial?
So like you escape predators, just like.
Exactly. In the same way that if a dog is chasing a cat, the cat can climb right up the tree where the dog can't go. If this thing is being chased by, there were sharks. If it was being chased by a shark, it could just go up on the land. The shark's like, gosh darn it, he went up on the land.
Oh, diddly dee, he
Oh,
escaped.
diddly dee, he escaped. Guess we'll go find something that doesn't have stout anal fins. And then, over time, these fish, and there are examples still today of these, lungfish existing, where their swim bladder, in addition to their stout little fins, their swim bladder has become able to provide air for them. Hey, listen, are you guys listening to me?
Yes, we are.
This thing, a coelacanth. The coelacanth there has been fossil for, but then in the 1950s someone found a living coelacanth, which has its swim bladder is different from other fish's swim bladder. In normal fish, a swim bladder just allows it to buoy, right? It allows it to go up and down in the ocean or the lake or whatever. In the coelacanth, it can use the air that's in its swim bladder to provide oxygen to its cells. So it could, we wouldn't quite say breathe, but it could survive on the land with respiration too, whereas the Tiktaalik would just be like suffocating when it was on land and it had to go back real fast. The coelacanth, and maybe not, this might not be the right word, let's not use that. I think the example your book is Acanthostega. Or possibly, no, Ichthyostega. Ichthyostega. Right, it could, like I said, breathe not quite, but it could survive on land in the air. The first example we have of what, can you guess what this is? No, fish, there have been fish for a while now. The very first example of a what that can survive on land and in the water.
Organism. Frog.
Which is a type of, this isn't a frog,
Amphibian.
it's an amphibian. This is the first example we find in the fossil record of an amphibian. But like we said at the beginning of class, because we're aware that only about 1% of organisms get fossilized, this may not be the first amphibian, but it's the first amphibian we have evidence for right now, right? Does that make sense? These are all called transitional fossils, right? What they do is they provide evidence for evolution, that life has changed over time, right? Because instead of just saying, we know there's a frog now, and we know there's a fish now, this shows us that there's a link between those, right? That one has in the past changed to the other. Does that make sense? Do you have questions about that?
No.
Do you have questions about
It
that?
went from one that can push to one that can go on land. to
Yeah,
one
right.
that
So this is pretty facile. How long would this whole process have taken? 20 years?
No.
9 years?
No.
90 years? No.
No.
Probably this whole thing took place over millions of years, right? And that's why we're comfortable saying that this does occur, because the time it takes is so dang long. Why is it faster? Why is this faster? Why is evolution faster for the little superbugs, the bacteria that have evolved not to be affected by our antibiotics? Why would that be faster for them than this for these complex organisms?
Because those organisms might live longer than the bugs.
Okay, these live longer and do what less?
Die less.
Yes, that's true, they do die less, but they also, what's another major part of life?
Live
Maybe.
in one.
Yeah, they reproduce. These reproduce slower and less. The faster the reproduction, like in bacteria where they're splitting all the time. Have you ever done one of those where you rub the swab on something and then you put it in the petri dish?
We tried that with bread, but it didn't work.
Okay,
The
point is, you know what I'm talking about though. The reproduction of bacteria is fast, right? They will grow from completely invisible to filling up that entire dish in like 2 days. Bacteria reproduce fast, and therefore they evolve fast, right? Their traits can be passed on faster than for these complex
like
organisms.
3 drips of water on bread, put it in.
The reason there is, one of the reasons that there's still consternation about this is that does it occur or not? Human beings have not existed for long enough to see this occur, to have direct evidence for large things to change, right? Human beings, it's not, the fossil record shows us that human beings have been around maybe 250,000 years. That's a long time. Civilization's been around for about 40,000 years. That's a long time. But it's not long enough to see Eusthenopteron turn into Tiktaalik. This would have taken tens of millions or hundreds of millions of years. Do you see the difference?
Yep.
Does this kind of make, are the bells ringing in your little brain? Does this kind of make sense to you?
Yes.
You have questions about it, Angie? Do you? You do, but...
I do, but I don't know.
How do the rocks help us? Because there's other rocks are evidence for geologic change too. How do the rocks help us?
How they.
What can we do with the rocks that we talked about in the last lesson?
Study.
We can study, but what process can we do with the rocks to tell us, that helps us learn about the history of life?
Cut them on.
Yeah,
What do we do? What kind of? You guys know what do we do with the rocks?
You study them.
Just study them how though.
You
We can
look
do-
at them.
Does anyone know what I'm talking about?
Nope.
Okay, let's go back in our book a little ways, because you really should rewatch that video, I guess, then. But we're talking here about, go back with me in your book to page 13, where we talked about radiometric dating. Does this ring a bell now? Radiometric dating, which is a kind of absolute age dating. This was about 2 weeks ago that we talked about it. But the rocks come in because many rocks have radioactive materials in them that we can date radiometrically, providing us an actual number year, right? We can say this, for instance, we find Tiktaalik fossil. This is an example. I don't know if this is true or not. But for instance, if we found Tiktaalik fossil, right, with its little stout fins, in a rock layer, right? Because we find fossils in rocks. Are you with me?
Yeah.
And we take a little chunk of this rock, and we find using radiometric dating that this rock is 250 million years old. That tells us also that what?
That the fossil.
That the Tiktaalik fossil is 250 million years old. And then if we find that above that, much above this fossil of Tiktaalik in its 250 million year old rock, we find this fossil of Ichthyostega with its little lung, right? We find this fossil of Ichthyostega. What does that tell us about the relationship between Ichthyostega and Tiktaalik?
They're related.
No, what does it tell us about them though?
They.
Which one's older?
That one.
Tiktaalik's older. He's pointing at Tiktaalik. Because of what? Because we know that the rock layers on the bottom are older, right?
Yep.
We also know that this one was 250 million years old. So how old must this one be? Less than that. It must be less than 250 million years old.
Yeah.
Okay. Does this kind of make sense? So where do the rocks come in? We can date the rocks to find a number age of the rocks. And then we can find the fossils in it, and we link it all together, and that whole thing is called the fossil record.
It is 249,999,000.
No, Justice, it doesn't have to. Where's your pet Tiktaalik at?
It's in my house.
It's dead. Why? What happened to the Tiktaalik?
It got old.
It died.
This specific one is dead. It's in the rock. But what happened to the Tiktaalik in general?
It's
It
moved
evolved.
on to become a
This went extinct.
whale.
Extinction. You know what extinction is. We don't need to define it.
I did.
Oh, what is it? Sorry, just find an extinction.
Dead animal. No
Oh,
longer
okay. So when the deer dies, it's extinct.
Yep.
No.
When the species.
Yeah, when everything of that species is dead, it's extinct.
How do you know?
Listen, this is the last thing we're going to talk about before it's time to go. We use mass extinctions. How might a mass extinction be different?
I have not a clue.
It would be multiple organisms.
Yeah, many species. Many species.
I'm not saying species.
No. Extinction is a species. But when many species go extinct,
That's a massive
that's a mass extinction.
dope.
And we use the patterns of mass extinction to separate geologic time. Look with me on page 35.
Didn't that?
Don't put your book away. Look with me on page 35. Page 35 shows us a table of the different mass extinctions that have happened on Earth. That there's evidence for on Earth. What might provide us evidence for mass extinction?
That they aren't here anymore.
Okay, that's a good evidence, right? The fact that they don't exist right now means that they're extinct. What is another evidence for a mass extinction? How do we know if it's a mass extinction?
You can't find one species. That's
Right, so if we look at this rock layer, and there's all these weird different little fossils in it, right?
That's Illuminati.
And they're not in this rock layer has different fossils, right? This rock layer has different fossils. We can tell that these ones have gone extinct because this one's more recent, right?
Yep.
And so when we see a lot of different kind of fossils all go away at once all over the world, that's called a mass extinction. And we use that to define the beginning of a new era or period of geologic time.
Dope.
Look at page 35. From the top, we have 5 extinction events that are listed here. What's the first one? These are kind of hard words to say. Ordovician-Silurian extinction event. How long ago was that? 443 million years ago. The next one was said Late Devonian, 354 million years ago. Then Permian Triassic, 250 million years ago. Triassic Jurassic, 200 million years ago. And then finally the Cretaceous Tertiary, 65 million years ago. What happened in the Cretaceous Tertiary?
They all
Died.
died.
Who?
I mean, they went to land and then they were.
Who all died in the Cretaceous Tertiary
The-
65 million years ago?
The man.
The dinosaur.
The dinosaurs. That's all about the dinosaurs. We'll talk more about these. We're going to watch a video that kind of explains all this to you in order. Whoa, hold up, Cyrus. I haven't said anything. We are done, but you sit down. We're gonna talk about this in the lab tomorrow, and I'm gonna check your explorations. Do you have questions?
Nope.
Nope.